right, think about the following questions. Why do you text? No, let's not consider that question just yet. So scientific notation has a lot to do with exponents, which we will see a lot, but the nice thing is that the base value, not that anyone remembers that, will be 10. So most of the time we're going to see 10 to some power, maybe like 5, something like that. So the nice thing about this is this would be just a 1 with 5 zeros. But in addition to these, we're going to be multiplying this by some other number like 6. Okay? Which means all I'm going to do is replace the 1 with a 6.
Oh my goodness.
So this would be 600,000, okay? Now, the problem with scientific notation is it's extremely scientific. The science people, feeling discriminated against, told the math people that they needed their own notation. So the math people created this for them, and then the science people stole the credit and said, well, we did it, when in actuality it was the math people. So
How do you know?
we were just trying to be nice, and unfortunately it came back to you guys, and now they feel like everyone needs to know scientific notation.
Wait, how do you?
Scientific notation, now let's look at that question. So think about the following questions. Why do you text? It's because when you text you can write stuff really quickly, very easily. As it turns out, scientific notation is the same way, even though we may not see it that way even after today or after the unit. But mathematicians created this so that the science people could have a quick way to do some of their calculations. And as it turns out, it saved them a lot of time, especially when dealing with extremely large numbers, like distances between planets.
So that's my weight.
Or extremely small numbers, such as the size of a molecule. Okay. The notation is the important part, Radicale. Scientific notation will always be, scientific notation will look like these. So we're always going to be multiplying by some base 10 to some power. Now sometimes that power is going to be negative, sometimes it's positive. It doesn't matter, but we're going to have a power up in here. And this number in the front, we'll say, I don't know, T. Alright, T. Sometimes T will be a decimal value, but if it is a decimal, it will only have one value in the ones place. So we can't have anything bigger than 9 on this T value. But we can have decimal values up in count. Some kind of decimal value numbers.
How are we supposed to write this?
See, if you have something bigger than 9, then it gives you 2 digits to the left of the decimal, but you can only have 1.
I'm still confused.
That is just formal scientific notation. Like this one up here, we would have the 6, right? So they'd probably put something like 6.0 times 10 to the 5th. This is formal scientific notation around count. So if I had a big number, let's look at this.
Then it would have to go to the right of the times thing?
No, not necessarily. So a big number could be something like 7.125. And then we'd multiply that by 10. If it was a big number, then it'd be 10 to maybe the 12th power.
Wow. Wait, 1 second.
So again, we have one value to the left of the decimal. We can have as many values to the right of the decimal as we want until the science people said that there's only significant numbers that we need to consider. So the table below includes numbers written in standard form. That would just be a regular number like, I don't know, 1. Standard form. Or if it was a decimal, 1.2. Okay, that would be considered standard form. Calculator notation we'll get into. All right, so calculator notation is just the buttons you would push. Like in A, you would push 1, 0, then the caret symbol, 0. The exponent notation would be something like 10 to the power of 0. And we know 10 to the power of 0 is 1.
It is.
Because anything to the power of 0 is 1. Next up, we got 10 caret 1, which is 10 to the power of 1, which would be 10. 10 caret 2 is 10 squared, which is 100.
No, you did it still.
Next, we got 1,000. 1,000 would be 10 cubed, because we got 3 zeros, which in calculator notation would be 10 caret 3. All right, next up, we got 10,000. There's 4 zeros, so we got 10 to the power of 4. Which again would be 10 caret 4. All right, so now we got 4 times 10 to the third, which is 4 times 10 to the third in exponent notation, which would be a 4 with 3 zeros. All right, now we're on G.
Okay,
So what is the exponent notation?
6 times 10 to the power of 5.
Excellent.
Yes.
And then what is the standard number?
600,000.
That's correct. All right, next up, 7 times 10 to the 8th, which would be 7 times 10.
It has
To the
8
eighth.
zeros behind it.
That's right, so we got a 7 with 8 zeros. So you guys see right there, we're looking at some pretty large numbers here, which is good, because scientific notation is meant for some really big numbers and some really small ones, which we'll get into. So this next one, this one is 8.1 times 10 to the third. So hopefully you guys realize at this point, it's not necessarily how many zeros you're going to have. It's how far you move the decimal. So this one, we're going to move that decimal 1, 2, 3. So we'd have 81, and then we'll fill in those 2 empty spaces with zeros.
Wait, explain that again.
That would be 8,100.
Move it.
If that 3 was a 4, then I would have moved
would
it
be
4 times,
81,000.
and I'd have 81,000.
Is that only?
That's the nice thing that science people like about scientific notation. Thank you, or you're welcome, science people. Is that the exponent for the 10 tells us how many times to move the decimal, which is really all we're doing. So finally, calculator notation for this last one: 4 times 10 to the 9th. Bam.
Is this for YouTube?
Here we go. Exponent notation for these. 2 times 10 to the power of 0, which would be the same as 2 times 1, which is 2. So notice on this one, the decimal would be after that 2 as well. And the exponent of the 10 tells us we're going to move it exactly 0 times, which we did, which is why we got 2.
Oh, I understand this. I actually get
Now we got 2 times 10 to the 1th. So again, we're going to move that decimal 1 time, which would give us 20.
Wait, will you?
Next up, this one is 10 to the power of 2, so we'd move that decimal 2 times. So we'd have the 2, 1, 2, gives us 2 zeros. Now again, this is giving us zeros because we don't have any decimals on these, which is fine. This next one would be 2 times 10 to the third, which is the same as 2 times 10 carried 3. So if we were to continue this pattern, then the next one would be 2 times 10 carried 4, which would be 2 times 10 to the 4th, which would be a 2 with 4 zeros.
I'm so proud of myself.
20,000. All right, so 4.2 times 10 to the third. So, in just, I guess, exponent notation, 4.2 times 10 to the power of 3. So again, that 3 tells me I'm going to move that decimal 3 times. So I'd have 4, 2, and then 2 zeros right account. All right, next up, this one would be 6.9er times 10 to the power of 5. So moving that decimal 5 times would give us 4 zeros now, because we had to move the decimal 1 place for the 9er. 690,000. Next up, again, 7.12 times 10 to the 8th, which would be a 712. So the 1 and the 2 account for 2 of the exponents. So then we'd have 1, 2, 3, 4, 5, 6 decimals. 6 more places to move the decimal. So 712 million.
Wait, what?
All right, next up.
Wait. I want to be able to do it at home.
All right, so this one still be 8.1 times 10 to the 4th. And again, we can see on this one, it was 8.1, but then we moved the decimal 1, 2, 3, 4 times to give us 81,000. All right, so let's fill in the rest of that. That'd be 3.9 times 10 to the power of 6, which would be 3 9er and 5 zeros. 3, 4, 5. 3,900,000. We just made up our own for that last one. So now let's write 2 things that we learned about scientific notation. The power of 10 tells us how many times to move the decimal, And number 2, there we go. So yeah, the power of 10 tells us how many times to move the decimal. The caret symbol is the power button. That's good enough.
Where's the easy?
Easy. All right, the definition of scientific notation, this is extremely formal. A number that is in scientific notation takes on the form a times 10 to the power of b, where a is called the significant figure, and, well, a has to be greater or equal to 1, but also less than 10, so it can't equal 10. And n is the integer. The number after the multiply, or 10 to the power of n, is called the order of magnitude. We're not so worried about that terminology or vocabulary right now, but what is important for you to know is that we can have one number, a decimal, and this number has to be not 0.
So 1 through 9.
So 1 through 9. And then you can have whatever decimals you want after that. We'll multiply that by base 10, and then we have some power radicand. That's all we really need to know. That's right. But now that we've seen the formal definition, I'm just showing you that's what it's saying, just in different, very nerdy words. All right, check these large scientific notation numbers, the standard notation, and vice versa. And we'll make a number for the blank cells, which we'll do. So standard notation is the actual number that this is. So, for example, I would move this decimal 8 times to the right. 1, 2, 3, 4, 5, 6, 7, 8. So I have 6, 3, 4, 5, and then 1, 2, 3, 4, 5 zeros. And then we can put the commas in there to specify some of the place values. So this is standard notation radicand. All right, the next one, we're going to move this 2 times to the right, but then 2 more because we got a 4 on my exponent. 8, 0, 4 with 2 zeros. 80,400. Next up, 4, 2, 6. So we moved it twice, but then we got 3 more. 1, 2, 3, 426,000.
Slow down, you're going too fast.
All right, so what number do you guys want in scientific notation over here?
54. No, 5.4.
5.4896. We'll do this times 10 to the power of 3, just to mix things up. So what would this one be? There we go. This is a standard notation for that number. Now we're going to write these numbers from standard notation to scientific notation. So this first one right here, we need to analyze this number. So first off, we got 5,320. We know the decimal has to be in front of or to the right of that first non-zero number. So the decimal is going to have to be 5.32. You can put a 0 there if you want. We're going to multiply this by 10 to some power, and we could see that it would have to move 1, 2, 3 times. So we got a power of 3.
Wait, so we
Bam. The 0 right here, some people say, is an insignificant figure. I don't really care because this is math, not science. Now, eventually in science, they'll say, look, this number is not really important because of the value that we're looking at. We're really only concerned with the tens because the object we're dealing with is so humongous. Okay? So the ones place is not really that important anyways. All right, so let's look at this next one. So I know I'm going to have this 4 right here. The decimal has to be to the right of the 4. And then I've got this 2 right here. Now this one I'm not going to list the zeros because there's so stinking many.
Yeah.
So I'm going to make this multiplied by 10. But I've got to figure out the power. So I would have to move the decimal 1, 2, 3, 4, 5.
Look at that, I did it!
There you go.
I don't think you did anything. Okay, so
You could do it by yourself, you know.
yeah. Okay, so we got this number that's between 1 and 10, so it's going to be our first number, 9.04. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 decimal places that we need to move it to, so we got to do 9.04 times 10 to the power of 9er.
Bam.
Boom. Easy!
I did the. Wait, what?
Let's make up our own number on this last one right here.
Wait, will the
All right, let's do this one.
will only be in the tens?
This is 932,100,000. All right, good luck.
Heck yeah! Hello, YouTube. We're going to be doing an equation. Okay, so we gotta put the decimal right there. Can you guys see that? Right there. And so, which means that it would be 9.321, and then the rest is 0. So we don't need to do that. Times 10. That's not a visible one. Okay, 10 to the power of, so 1, 2, 3. Oh wait, I should draw that. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So it'd be to the power of 8.
That is correct.
This is correct.
Excellent work. Now try these small numbers. See if you can figure out the method. One example is given. Make up a number for the blank cells. All right. Now, it's been mentioned already that if the exponent is negative, then we're moving the decimal to the left. So this 4.2, we're going to move this to the left. 1, 2, 3, 4, 5, 6, 7, 8. And that would give me 7 zeros, so I got 0. Now those zeros are to the right of the decimal, so 1, 2, 3, 4, 5, 6, 7. And then I have the number that I originally started with, the 4 and the 2. Now I space every third zero out there just so we can see some place values. However you do it is up to you though. Yeah, so that's because there's no commas right
So
here.
you move it to the left now.
That's correct. With negative exponents, we're moving to the left. So on this next one, to the left 7, 1, 2, 3, 4, 5, 6, 7. So I'd have 0.1, 2, 3, 4, 5, 6 zeros. 1, 2, 3,
Wait, why 6?
4, 5, 6.
Because you move it 6 times.
And then I've got the 8, 1, 2.
Because of the decimal.
Bam. Alright, so these ones are going to work the same way. It's just, again, the exponent is going to be negative on these. So for example, I got my 7 right there. So it's got to be 7.5. Because that 7 is the number farthest to the left that is not 0. And I'm going to have to multiply this by 10. So multiply this by 10. And the power is going to be 1, 2, 3, 4. But again, it's going to be negative 4 because I'm looking at a full decimal value in standard form. Alright, so this next one. This one is 4, so I got 4. Point. Yeah, I would have to include the 5 there. And this would be multiplied by 10 to some power.
To negative 6.
1, 2, 3 to get to where the decimal is. So that would be a negative 3 right here.
Oh, I was going. I just say okay.
Alright, 6. This one, we only want 3 significant figures on 6. So what that means is I only want the 3 numbers farthest to the left, which in this case is 4, 5, 3. Now the other numbers I would fill in with zeros. Again, this is important to science people because they say, well, the other smaller numbers aren't so important because we're looking at something extremely large. So this number now, in scientific notation, would be 4.53. We're going to multiply that by 10 to some power. Well, what power? 1, 2, 3, 4, 5, 6. 10 to the power of 6.
Oh, wait, I did negative 6. Oh, this is puzzling.
Now, you guys see why this one's positive?
Yeah.
Right here? Because the number we started with was not a decimal value that's smaller than 1.
Yeah.
Alright. On C right here, we'll change this to scientific notation as well. So once again on these, we're going to move the decimal 3 times to the left. 1, 2, 3. So I would have 0 point, and then I got 2 spaces to fill with zeros, and then 7, 6, 2, 5. Now on this one, this is the same as the last one, except again the exponent's going to be a little bit different. Alright, so I'm on G right now. So G, we know the decimal needs to go between the 9er and the 2. So that would have 9.2. Then would multiply this by 10. And to find the power, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, but this one, since the value we started with was less than 1, we're going to have a negative exponent on that. Alright, so on 7, we got to express this number in scientific notation, but we only want 2 significant figures. So scientists say, well, some values are so insignificant that we just don't count them in there, okay? So what this means is we're only going to take the 2 numbers farthest to the left that aren't 0, which in this case is 4 and 5. That means the other numbers will just be zeros right here. Now this is 0.00045. And since it's a decimal, we could ignore those as well. So if we wanted this in scientific notation, we'd put the decimal between the 4 and 5, giving us 4.5. But then we'd multiply this by 10 to the power of 1, 2, 3, 4. But since it was a decimal, it'll be negative right there.
You lost me.
Wait, why didn't you use the...
Take a moment in your calculators, do 5,555,555,555 multiplied by itself, and then tell me what it says. Now some of you guys have calculators that are actually showing you the scientific notation for this, but if you have some older versions, it'll give you what is called this. This is E notation. E notation is the same as scientific notation, but instead of showing the multiplied by 10 to the power, they just put an E there. So if we rewrote this, and we wanted it in scientific notation, would have multiplied by 10 to the power of that 19 right here. Now this is in scientific notation. So this is the only difference between the two. Some of you guys do have calculators that showed you this in scientific notation, which is okay as well. Some calculators can give you answers in scientific notation, but other calculators have different ways of displaying scientific notation. One way they can display scientific notation is 3.08e to the 19, which means 3.08 times 10 to the power of 19. So write this number in standard form. So we'd have the 308, and then that would be moving the decimal twice. So from here we need 17 zeros. 1, 2, 3, 17 zeros. Now again, this is an extremely large number, and if we put the commas in there, we'd have to have them up in here. Every third one.
This wouldn't even show up on a freaking calculator.
That's right. The calculator is not going to show this. The calculator will either show this. Now we do have some calculators though that will actually show the scientific notation.
That's a big calculator. That's
But on the test, you guys are going to see some of these where it wants you to show this E notation, which is what this is called, E notation, in scientific notation and standard form. So this next one, a calculator gives you an answer of 5.025 E negative 3. So in scientific notation, this would be 5.025 times 10 to the power of the negative 3. Now if we wanted this in standard notation, that negative exponent tells us we're going to move the decimal to the left. So this would be 0.005025. And explain why these numbers are not written in scientific notation. This one right here, this number, the problem with this 402.2, why it's not in scientific notation, is because we got 3 numbers to the left of the decimal. This one would have to be 4.022 to some times 10 to some power, okay? The decimal's in the wrong place for this one. This one as well, the decimal needs to be right here.
So what we're doing right now,
And the decimal's in the wrong place. 14, observe the numbers given below. If the number is written in scientific notation, we'll circle it. If it's not, then we'll change it to scientific notation. Try to think about how many spaces you will have to move the decimal and how that will affect the exponent as well. All right, so let's find the ones that are first. So any of these that have a decimal after the first number to the left, then is good. So this one doesn't work. A, B is no good. C is no good.
and F are good.
D is not good. But E, this one is already in scientific notation. Because the decimals after the 6, we got a 10 to the power of something.
Wait, A is not correct?
F also is in scientific notation.
It was
Alright, so what about these other ones? We do need to change these to scientific notation. So in scientific notation, the numbers are inversely related. If we make one smaller, then the other one has to get bigger, and vice versa. If we make one bigger, the other one has to get smaller. So this one, see, this is 348. We're going to make it a smaller number, 3.48, which means the power of 10 has to get bigger by 2 decimal places, which would be 10. Alright, so B, this one once again, this one is a very small number that we're going to make bigger, 4.026. We're going to multiply it by base 10, but since I made that small number, that very small decimal value, a bigger value, I'm going to have to take away 1, 2, 3 spaces from the 9, which would be 10 to the power of 6. Alright, so C,
I understand it now.
this one needs to be 7.42, right? Because that's where the decimal needs to be after the first, or the number farthest to left that's not 0. So we're going to multiply this by 10, but we're going to make the small number bigger by 3 decimal places, so I got to make the exponent smaller by 3
So that equals
values.
-6.
So that would be -6 right there.
So okay. So I just went the wrong way.
wait, wait.
The calculator give you an answer of 9.22e to the power of 8, or just e8. We want to write this in scientific notation, so just like the one we just barely did on that last page. We still have 9.22, but now this is multiplied by 10, and the power of 10 is after the e there, the 8. But then it wants this also in standard notation, standard form. So we got 922 with 6 zeros. 922,000 million, rather. 922 million, that's better.
Good job.
Enter the following problems in your calculator. Write the answer in scientific notation and standard form. Express your answer with three significant figures. Most of you guys have calculators, like on a these. You can use the parentheses directly on that, and it will show it to you. You can type this whole thing in, and it'll give you the answer directly. Alright, so if my calculator gave me scientific notation, it gave me this. But if it didn't, then it would have given you the standard form number. 575, 1, 2, 3, 4, bam. 5,750,000. So the calculator gave you this number in red. I kind of did the work in my calculator on scientific notation, which is why it gave me this scientific notation. By calculator, I mean I did in my head. But if you guys got the standard form number, you guys already know how to change this into scientific notation, which is how we would have gotten these. Oh, by the way, now remember, only if the number is so big will it give you the scientific or E notation right away. But this one wasn't big enough for it to give us the E notation. Alright, B, what did you guys get on your calculators? Alright, so if the calculator gave you these, negative 539.68, that's the standard notation. The scientific notation would be 5.39968. This is negative, by the way.
I forgot.
So we'll multiply that by 10 to the power of, we moved it twice.
Okay, I got it now.
So that would be, yeah, to the power 2. So see, when we multiply those in the calculator, we get 280,000. Again, we're just typing that in straight across, and then we would change this to 2.8. Yeah, times 10 to what power? 5. Nailed it. The diameter of a human hair is that many meters long. Write this number in scientific notation. All right, good luck.
First, you have to move the decimal all the way over here. Oh, whoops. And then, oh no, whoops. And then it makes it 9.9 times 10 to the power of negative, because you moved it this way, 1, 2, 3, 4, 5. Boom.
That is correct.
Wouldn't it be 6?
No, because he moved it 5 times only. So this would do.
Can I do a YouTube one?
The mass of a snowflake is approximately this many kilometers, very small. Write this number in scientific notation. All right, very good. So we got 3, because the decimal is just going to go to the right of that 3, times 10 to the power of 1, 2, 3, 4, 5, 6. So yeah, it's going to be -6 right there. And this one specifically is in kilograms. If you're only concerned about the mass of one snowflake, circle the unit below that would best represent the quantity. Convert the mass of the snowflake to your chosen unit of measurement. All right.
Milligrams.
So as it turns out, since we moved the decimal place 6 times, I would say milligrams would be the best unit. Kilograms was so small amount of kilograms, but even grams you're going to have a very small amount of those. So milligrams, what that would do is that would move the decimal 1, 2, 3, 4, 5, 6. Yep, 6 times. So this would be 3 milligrams on this. 3 milligrams would be the conversion. Suppose there are approximately 1 million snowflakes in one giant snowball. What unit should you choose to represent the weight of the snowball? Well, if there was 1 million of them, that means you'd have 3 million of those milligrams. That, by the way, would give you 6 zeros. And yes, I am looking at the chart. So, that one I would say would be kilograms. Find the mass, that would be 3 kilos. A snowplow is moving snow from a parking lot, dumping it into a dump truck. One unit of measurement would be the most appropriate to represent the weight of the snow in the truck. Well, if they gave us the option for tons, we would, but since they didn't, we're just going to have to look at kilograms. Metric tons, it really doesn't matter. That'd be a better appropriate value to use. So this one has Facebook worth $2 billion. Write this number in scientific notation. Done. Here we go. So it's going to be 2. You can write 2.0 if you want. We're going to multiply that by 10. And then how many zeros is there?
1.
9.
Oh, I'm not.
There it is. That's in dollars.
Or could you do this?
A computer radio station stores all the station's music digitally. The computer can display the amount of time it will take to play through its entire library of music.
Wait, if you don't get them done.
Alright, the DJ can choose if she wants to display this total amount of playing time in seconds, minutes, hours, or years. The radio station has about 7,000 songs on the computer that have an average playing time of 3 minutes for each song. Calculate the total amount of music in minutes so that the radio station's computer, write this number in scientific notation. So we got 3 minutes worth of 7,000 songs each.
So it's 10 to the power 3.
So this would be 21,000. Oops, I wrote that backwards. 21,000 minutes. Now this is not scientific notation, this is standard notation. So we'll just change this to 2.1 times 10 to the fourth in minutes. If the DJ is planning a playlist for the entire week, should she display the total amount of time in seconds, minutes, hours, days, or years? Convert the playing time into your desired unit of time. Well, if it asked me to, then I'd say minutes because I've already done it. But let's say that we're going to do this in hours then. Because we can do 7 days in hours, but whatever. Convert the playing time into your desired unit of time. So we got 7 days. We're going to convert this into hours. So this would be the same as 7 days of 24 hours, which would give us 14, 16, 168, 168 hours in a week. So 7 days a week, 24 hours a day, 168 hours. Bam. There we go. We converted the playing time into our unit of time. A seafloor spreads at a rate of 10 centimeters per year. If you collect data on the spread of the seafloor each week, what unit of measurement would be most appropriate to use? Convert the rate at which the seafloor spreads to your chosen unit of measurement. So it's spreading at 10 centimeters a year. We want to see how much it would spread each week. So if it's 10 centimeters, we would want something smaller like millimeters. Now we need to convert the 10 centimeters into millimeters. And it would take 10 centimeters just to make 1 millimeter. So that would make 100 millimeters. And that's per year, by the way, not per week.
No, I just that's just what I did.
See, if we want it per week, right, we usually gauge a year to have 52 weeks, so we divide that by 52, and we could see how many millimeters it moves every year. Week, rather.